Okay, so RC circuits. Um, so we start with both the resistor and the capacitor in the circuit and just a DC battery. So it's going to look something like this. Capacitance, the voltage on the battery is here, and a resistor in the battery like that, in the circuit like that. Now we already know that, once I close the switch, just remind ourselves what happens with the capacitor. Um, we said that even with in an ideal circuit where there's no resistance, ultimately, as the capacitor charges, excuse me, as the capacitor charges, it develops a voltage, has the opposite polarity of the battery, and so the current will die down. So as soon as I close the switch, the current is a maximum. It starts to charge the capacitor. Capacitor charges up, opposite polarity, as I said, and as that happens, it's pushing back against the current. Ultimately, when the voltage of the capacitor is the same as the voltage of the battery, which it will be if there's no resistor in the circuit, then the current just stops and the circuit is kind of frozen, so to speak. But with a resistor in the circuit, the energy will bleed off. Like as the charge goes around, I guess the capacitor will start to charge, but ultimately, I guess the same thing will happen. Eventually, the capacitor will charge up, but it just does it much more slowly because some of the energy is being dissipated as the charge goes through the resistor. And so we're going to apply a voltage rule, and it'll give us a differential equation. And it turns out that's a differential equation that we can solve with the methods of this level of mathematics that we have here. And it's a method called separation of variables, which it's the same kind of process, a similar process to last semester. I used separation of variables to handle friction for a free-falling problem with drag, drag force. And so if you've had me before, you've seen this technique some previously, but we're going to apply it here with the rules of the voltage rule. And once we have the vote, we're going to apply it basically to a circuit. So let's go ahead and do it. So we have the voltage rule. Voltage rule is that we start anywhere in the circuit and we go all the way around and we add up all the voltages. So if I start here, for example, I'll start here. And we'll just go around the counterclockwise in the clockwise direction to different positions. So we can label them maybe 1, 2, 3, 4, just different positions in the circuit. Going from 1 to 2, I'm going to go down the voltage hill because I have positive to negative. So that'll be a negative M for the battery. And then going around, well, if this thing is charging, so this will be the positive plate and this is the negative, right? Following the holes around the circuit. So when I go through the circuit from 3 to 4, I'm going up the potential hill, so it'll be a plus capacitance. Now remember, just do a little side note here. Remember that the definition of a capacitor is actually, well, I should probably do that here actually. Sorry, let me get some stuff here. Um, I'm going to start by reminding you the relationship of voltage to capacitance and voltage to resistance. So we'll start with the definition of capacitance is that a charge equals it's charge divided by voltage. So then voltage is equal to charge divided by capacitance. And for Ohm's law, voltage is equal to the current times the resistance. Now I'm going to write the current as an I, as a small I, because it's not constant. And in fact, just to illustrate, emphasize the charge, we're basically in the circuit between the time that we close the circuit and the capacitor charges up. So during that time, both the charge on the capacitor and the current in the circuit is changing. So it's not a steady state current, right? So we're going to call that I of t. And we're going to call the charge on the capacitor Q of t, implying it's now a variable. We're in the process where it's a variable. So I'm going to write this more like 1 over C times Q of t, just to emphasize that both the charge and the current are changing. Now, let's go ahead and apply the Kirchhoff rule again. So coming from this point, 1 to 2, I have minus. I'm going down the potential hill. When I come here, I'm up the potential hill, but I'm going to write that as 1 over Q, 1 over C, 1 over C times Q of t. Actually, I need more space. So we'll put this over here. So minus M for the battery plus 1 over C Q of t. And then when I go through the resistor, well, whenever we go through a resistor in the direction of current, that's a voltage drop. But I've said the current is actually going in the counterclockwise direction, and I'm traversing in the clockwise direction. So when I go through the resistor from 4 to 1, I'm going through opposite direction of current. So that's plus the voltage across the resistor, which is I times R. And so I'm going to write that as a plus I of t times R. And then when I get back to 1, my total change in voltage should be equal to 0. Okay, so I have two variables, I and Q, and I want to apply something called, this is a differential equation, and I could apply something called separation of variables in order to solve this differential equation. Yeah. So it means that I want to get everything with I get current stuff on one side and everything with charge on the other side of the equation. Charge stuff or things that have units of charge. So there's a little bit of a trick of actually, let me go one step further. I'm going to take the E on the other side and I'm going to, actually, yeah, it's not going to be current and charge. It's going to be charge and time. But before I do that, I actually forgot one here, the definition of current. So I'm going to remind you of that here, that current I of t is equal to Q of t, or basically the derivative of Q of t, right? So it's going to be d dt of Q of t. So I can write the whole thing. In that case, the variables will be charge and time. And so I want to get charge on one side and time on the other side. So I'm going to stick that in and I'm going to manipulate this by taking it on to the other side. So we're going to get basically 1 over C. Well, I guess we could write it like this. It's like a first order differential equation. So we'll have, I'll write this term first. D dt Q, dq of t dt times r. So that's the current term. And then the charge term plus, q of t over c, taking this on the other side equals the m. I need more space. I'm making this too big. Let's come over here. So now I'm gonna separate variables, and I'm gonna do that. Yeah, I'm going to. How do you do that? Yeah, I'm gonna divide through by r. I'm gonna divide everything through by r first. So that will give me dq. I'm going to drop the time dependence just for space, the explicit dependence. Then plus q over rc equals m over r. Okay. Now I'm going to actually I'll put it back in. Now I'm going to take this term q of t over rc over on the other side. And then I'm going to have d dt of q of t equals e over r minus 1 over rc q of t. Yeah. Okay, this is it. So now I'm going to, yeah. So now I'm going to divide a little tricky. I'm actually going to cross multiply. That's what I'm going to do. Over here, I have everything, like the numerator is charge stuff, differential, a change in charge, and the denominator is a change in time. This is actually dq of t over dt. So, and if you look here, basically, this has units of current, so that's kind of charge stuff. And this actually would have units of current as well if you worked out the units. So this is kind of like charge stuff, change in charge, right? And basically I can treat this as a quantity that has units of I guess amps, which is associated with current and associated with charge. So I'm going to divide that whole thing, divide both sides by that whole thing, and then multiply both sides by dt. So on the left side, I have everything associated with charge, and on the right side, everything will be associated with time. So it's kind of like dividing through by all of this, which is going to come into the denominator on the other side, cancel out of there, so it'll just be a 1 on that side. But then when I multiply everything through by dt, I'll cancel the dt over here and bring it to the numerator over here, like dt over 1. So when I do that, and I'm just going to write it just so that I have dt on the right side, I'll end up with something that says, equation that dt over 1 equals dq dq of t, it's a variable, divided by all of this stuff, which is E over R, and that's a minus 1 over RC times Q of T. Okay. And one last thing I'm going to do now, I'm going to divide out, factor out an R of C from the numerator. And I'm then going to bring that thing over on the other side, because that's actually has units of time. And right, this does have units of current, right? Because this would be charge divided by units of time. And so we can work out that to show you that the units of resistance times capacitance is a unit of time. So I'll have dt is equal to dq of t. I'm going to have a 1 over RC out here. In the denominator, then I will still have to have, I'm going to have a E times R, right? Wait, what? Oh, no, the C is there. So if I multiply back through, this would have to be C times. All right, so because when I multiply through, I have E over R, right? And then minus, and then that's just Q of T. So now we're good, almost. Because this has units of charge, that's charge are coulombs, and this is coulombs and coulombs. And so if I just take this on the other side, then all that'll be units of charge and everything over here units of time. And you can see that this is Coulomb because it comes from the definition of capacitance, right? Capacitance equals charge times voltage. So if I multiply through by voltage, then it has units of the right, be voltage times coulombs is charge, and right side is charge as well, coulombs. Or voltage times capacitance, excuse me, is the units of charge, which has units of, is yeah, has voltage times the capacitance has units of coulombs, which is that of charge. So I just need to multiply the RC over on the other side now, and I'm going to have, actually, I'm multiplying 1 over RC. All right, so because this is 1 over RC. So when I multiply 1 over RC, I'm going to get dt over RC equals dq of t over c times minus q of t. All right, and so variables are separated. Actually, yeah, RC. So I guess you could, yeah, get my T here for a second. Okay. So variables are separated here in this equation. And yeah, units of time, RC. So how can we do that? Mm, so I can break that down for you. For obvious reasons, so notes, RC as units of time, which is um, so remember that resistance is well, it's ohms, right? So we're going to have ohms times capacitance, which is a Faraday, but that doesn't really make sense to you. You got to break it down. A farad, that is. So, well, the definition of resistance is the resistivity times the yeah, let's just remind you of this. So again, this one, resistance is equal to resistivity times the length divided by an area. So an ohm and resistivity is units of um, oh gosh, I'm drawing a blank, aren't I? It's going to be an ohm resistivity. What is that? It just comes directly from this guy. So it's an ohm times a meter. That's going to help us. Ohm times a meter. And capacitance is Coulomb per volt. That doesn't really help directly. What is the quickest way to show that this? I might do it here someplace, but maybe later. Sorry, I didn't put that. Still that RC has units of time. Okay, well, I didn't do that. Where's the quickest? Let's see. Yeah. Wow, folks, I'm drawing a blank. Um, I'll get a book real quick. It doesn't break down so easily. obvious fashion. Yeah, maybe I could just follow it through. So basically, RC, we're going to have an ohm. RC is going to be an ohm times a meter, and then times a coulomb over a volt. Now, here's time is going to come in here. Like a volt is equal to a a volt is equal to an ampere times an ohm from here. Okay, so an ohm times a meter and coulomb over ampere per second. Ampere times times a ampere times an ohm. Ampere times an ohm. So the ohms will cancel here. Actually, sorry. Resistance is not an ohm meter, that's resistivity. A resistance is just ohms. So sorry about that. Because this will be ohm meter times, and this thing here has 1/meters. So ohm meter times a meter is just an ohm. Sorry, I just got twisted in my head. Yeah. So that's it then. I got it. So this is just an ohm here. It might not be obvious yet, but we're done with this. So ohm coulomb per volt. So there's no meter here. So now the coulomb, the ohms cancels. But because of the definition of current, an ampere is coulomb per unit time, right? Just, I don't know wherever that is here, coulomb per second. And so that's it. You get that, that this guy then becomes a coulomb over a coulomb per second. So then the coulombs cancel. You have 1/1/seconds, and that just becomes RC has units of seconds. So RC is a time. It's a time. It turns out it's going to be when we solve this differential equation, one of the constants that comes out of it is a time constant, and that time constant will be defined as the resistance of the circuit times the capacitance of the circuit. So, and it will be a specific time. In fact, that's going to be a kind of a little problem I'm going to ask you about once we get the solution. We use that to that has significance, and we'll have to wait till we get to the end to see what the significance of the time constant is. So, all right. So that's just a little aside there. But we're back to this differential right here, equation 11. And it's, a separable equation. When you get to differential equations, you're going to study this. This will be probably one of the examples I'll talk about. And this differential equation is a very specific kind of differential equation, homogeneous, first order, something else, separable. I don't know. but there's something else qualification, which means that you can use this method of this technique to solve the differential because it's that kind of differential equation. Because the differential equation has those specific properties that allows itself to be solved in this fashion. Separation of variables. So the variables are essentially separated. Everything on the left side is time, and everything on the right side is charge. And those are the two quantities that are varying in the circuit: time and charge. Yeah, or something associated with charge, current. So now that they're separated, the only thing to do is just integrate both sides. Now, technically, you're supposed to do it with indefinite integrals, so you get the constants, and then there's a way that you apply what's called boundary conditions to the equation to get the value of the constants. But I'm going to cheat. Physicists do this all the time, and I'm going to put in limits. I'm going to take which are reasonable. I'm going to take the left side will go from t equals 0, so that as soon as I close the circuit, that's when my time starts, and at that point, well, just let it. So I'll go from t equals 0 to some arbitrary time, maybe when it's just sometime later, some later time in the circuit. And over here, when I close the circuit, the current is a max, but the charges on the capacitor is 0. And so as time passes, it's going to charge up. So I'm going to take the charge from Q naught to some later time. And it doesn't have to be before we were doing it. We were either doing it was fully charged or not charged. Here, because I'm in that time period, when it becomes fully charged, then the current will stop. So I'm kind of in that regime where the current is changing and the charge is changing. Again, to take the analogy back to mechanics, when we first started with free fall problems, we just said that when you drop an object, the velocity is 0, and the velocity is 0, and the acceleration is a maximum. And then it falls, it's falling in free fall, and we kind of just did problem when there was no drag, it just starts to fall at that same acceleration and speeds up. Acceleration to the gravity, and the object speeds up. But when we put in drag is proportional to speed. So the faster it goes, the larger the terminal speed. Sorry, the larger the drag force. But because there's something that's now balanced, that's opposite, a force that's opposite the force of gravity, at some point that drag force is going to get large enough that it equals the weight. And so, whereas with free fall, the acceleration is constant, with when you consider air, friction and drag, then the acceleration changes. It decreases and goes to 0 as the object falls, even though the object is still gaining in speed. So it gains speed slower, and then there's a top limit to the speed called terminal speed. And so as the object falls, its acceleration is decreasing to 0. The velocity is going from 0 to the maximum, because it has a maximum now. Technically speaking, with no air, there's no maximum. The velocity will just continue to increase as it falls. But with air, the drag force ultimately equals the weight. And from that point on, the object continues to fall, but it falls at a constant rate. And so when you apply separation of variables to that problem, you're actually finding the equation of motion in the regime where the object is falling from its 0 velocity to its terminal speed. So it's in that regime that the equations of motion apply. And from that point on, from the terminal speed, it's a different problem. It's not even the accelerated motion problem, it's the constant motion problem. So and so the analogy here is that once the capacitor is charged, that's a different scenario for the circuit. But during the time when the capacitor is going from 0 charge to maximum charge, whereas there's no resistance in the circuit, resistance acts kind of like drag in the circuit. So the analogy is that when there's no resistance there, it's just a constant rate. The current it charges up at a constant rate, which is the value of the current. But whenever the resistor is in the circuit, the rate at which the current is changing at which the charge is changing changes. So the current goes from a maximum to zero, just like the acceleration in free fall goes from g maximum to zero, and the charge on the capacitor is charging. Well, yeah, I guess basically, the difference here is that whenever the charge current goes to zero, then the capacitor stops charging. In the case of the free fall, the object will continue to fall, but it's kind of a different regime of the problem. So here, yeah, I guess you just say that the charge is on the capacitor, but it's maximized and that doesn't continue to change anymore. So this differential equation really just shows it just applies during the time when I close the circuit and the current is now changing and the reason the current is changing is because energy is being dissipated through joule heating from the battery, where that's not the case through the resistor, and that's not the case when the resistor is there. So it kind of acts, it's taking energy out of the circuit even as the capacitor is charging. So it causes the capacitor to take longer to charge. In the same way, yeah, whatever. I don't know. Yeah. So that's what we're doing. So then, yeah. Okay. All right. So let's just go ahead and knock this out. It shouldn't take longer than is necessary. So I'm going to go ahead. I guess this I didn't really need to have. This is just kind of an aside here. So now that I've proven it, I'm going to take it away. And yeah, I'm going to keep with the derivation. So we're going to come here and like I said, we're going to integrate now. So I'm going to integrate. So now integrate equation 11. Equation 11. And the right side, I'm going to go from t equals 0 to t. And over here, I'm going to go from q naught basically equals 0. It doesn't have to, but whatever. I'll just say q naught to q of t, the charge on the capacitor at some later time. So the left side just integrates to t. That's pretty easy. So we get, where am I? Okay, so I just basically have, 1 over RC times T. So it'll be T from whatever, T naught to T whatever. But the right side, it's basically it's log, right? Because yeah, so recall, in fact, let me remind you up here. So remember that the integral of, so recall that the integral of dx over x is equal to log x plus a constant but the integral of dx over something like a minus bx is equal to minus 1 over b times the log of a minus bx plus a constant. Now, in our case, I guess I could take out a minus sign, but I could just leave it in there. So in our case, the b is a minus 1, and the a is capacitance times the voltage. And actually, I did an indefinite integral here, didn't I? In my notes. But I didn't take the shortcut in my notes. You know what? I don't want to mess this up and try to do it in my head or whatever. So I'm going to go back and do this. I'm going to do this. I'm going to do this as an indefinite integral. It still works out. Just a few more steps. So again, just integrating as an indefinite integral. That's the most full-blown way, you know. So yeah, and it's not a big deal. It's simple for this type of problem anyway, so it's all right. Just puts a few more steps in the problem. Now I need space, so sorry. Okay, so the left side then integrates to, it's just going to be, t plus a constant, and this R1 over RC, that's a constant itself, so it's outside. So the left side of the equation, I'm going to get T over RC. Now, it's really 1 over RC times T plus a constant. I'm going to call it constant 1. But when I multiply through by RC, I'm going to have T over RC plus C1 over RC, which is also just a constant. So I could just write that as a constant. People do that. I don't have to write the C1 over RC because it's all just a constant. And but I'll do that in the next step. And on the left side, I'm going to have basically have to apply this formula. And if I do that, I'm going to have minus the log of quantity E times C minus Q of T, and then times, plus a constant. Now, I'm going to go ahead and act like I multiplied this through so I don't have to write the whole thing again. So basically, that's 1 over RC times, I'm just going to call that constant 1. It would actually be a different constant than the one that came out of the integration, but it's still a constant, and I'll have to apply boundary conditions to find them. Now, yeah, we're good. So now what I'm going to do is I want to get all the constants together. You can do that. So I'm going to take C1 over on the other side. So I'm going to have T over RC is equal to minus log of, technically this minus sign multiplied through as well. So in that constant, but I can just bury it in. I don't have to put the minus sign explicitly out there. Q over, and then that would be C plus C2 minus C1. I'm going to come down here and I'm going to define. I know you might not have seen this before unless you're in differential equation, but you can play around with the constants and name them whatever you want. So that's cumbersome. So I'm going to define a new constant. Chi is equal to C2 minus C1. And I'm going to take the minus sign, this minus sign, over on the other side. In fact, I could have kept that in parentheses. I should have. That's a little bit deceiving. Well, actually, Okay, yeah, technically, I guess, yeah, just so I'm not on the same page here. Yeah, just minus my Achilles heel. I just want to be careful about this so it's not confusing. I'm gonna go ahead and take the minus sign over right now. And if I do that, then I'm gonna have minus T over RC minus C1 equals log of EC. In fact, this should have been like this. I was going to do it like that. Minus QT plus CT. So now I'm going to have minus T over RC equals log EC minus QT plus CT plus C1. And now I'm going to define chi as CT plus C1 and then substitute that in. So minus T over RC equals log of EC plus Q of T plus chi. You know what? Oh my gosh. In my notes, I actually multiplied it through. So that would have been a minus 2, and this would have been a minus. And so then I would have had minus, and so then this would be basically C1 minus C2. I just want that to be C1 minus C2. So still substituting in and we're good. All right. I could have done it any of those ways, but I just want to do it the way I'm doing it so I don't screw myself up with get mess a minus sign somewhere. And you could, they're constants and they're arbitrary at this point, so you can define them however you want. Okay, so now I have defined this in terms of one constant. So this is a differential equation. So, and I think we might have talked about this a little bit before. Well, I know it was last semester with whoever. So the thing about differential equations is that you you get this thing here, this equation 16, which represents what's called a family of curves, family of solutions for this differential. And the family is kind of defined by the constant. And so if that infinite, it's basically an infinite number of solutions, but I only want one solution, the one that corresponds to my problem. And the one that corresponds to my problem is determined by essentially something called boundary values in math. In physics, we call them initial conditions because they're the initial conditions of the circuit that you're defining. Because that dictates, it's kind of like astrology. I don't know, in my mind, for some reason, I always think of that when I first learned this. Now, I'm not saying astrology is a science, okay? People say it's a pseudoscience. I'm not going to get into that argument. But the point is that the idea, the idea that when some sort of energy, soul, whatever you want to call it, is comes into this plane of existence, because everything in the universe is energy, stars, galaxies, everything, like energy affects energy. And we know that these fields, and this is kind of a side note, but just kind of explaining how I think of this and how a good one way to think about what a boundary condition does in math and these problems is thinking about the so-called, idea of astrology. And I'm not being facetious. I'm not saying one, I'm not being one way or the other. I'm just describing the thing. And I'm not going to indicate what I think about it. That's not the point here. But the point is that the idea is that we do know in physics that everything is energy and energy interacts. And even in terms of fields like gravitational fields, electric fields, they're not zero until you get to infinity. So it is not unreasonable. In fact, it is actually factual that right now we are being affected in some way by all of the heavenly bodies around us. They all have gravitation, they're, a lot of them, the masses of black holes, stars, planets, everything. And according to the universal law of gravity, the effect of their gravitational field, although it might seem minimal to us, because for obvious reasons, is technically not zero until we're infinite distance away, and we will never be infinite. Well, we're not infinite distance away if you can see them. Same thing with an electric field and a magnetic field, all of them, all the fields that we know, all the conservative fields that we know. So if our existence, our consciousness, ultimately, I don't know if it has been yet, I don't think it has, but it's defined in some way as some physical quantity, it certainly, in the moment that it is comes into this earth plane, it is certainly being affected by, everything, the position of all the heavenly bodies, so to speak. Now, that's a fact, science, straight out. Now, the idea that that now then dictates what the proclivities of that entity, that consciousness, I can't confirm that one way or the other. But what I can confirm is that that is a pattern everywhere in science. And that is actually what's happening with this. Think about it. In when you get a differential equations, this is like in chapter 2 or 3, they talk about this idea because separation of variables is the first technique that you learn to solve differential equations. And so this, if you graph it, right, if you were to graph charge per time, it's going to give you, say, in a certain range of time, it'll give you some pattern. Maybe it's like that. But the constant, it just changes the pattern. So you get this family of curves where, because the constant could go from 0 to infinity or whatever, positive or negative. And so depending on that constant, it's just giving you a curve, same shape, but just different, you know, different starting an initial position, in that in a certain time frame. And so what you're doing is you're picking out, when you apply the boundary conditions or the initial conditions of the circuit, of all those infinite possibilities, you're picking out the one path or the one path, um, one functional form or one solution essentially that applies to this specific problem. And so for me, I can definitely see kind of an analogy there with astrology, right? Like you have a specific initial conditions of the universe as this entity comes into existence in a specific place. And there's an infinite possible, because that, entity consciousness has free will, it has an infinite number of choices that can make. But there's some choices that, and that's where it kind of, digresses, that maybe have more of a proclivity because of the initial conditions of the universe, which are affecting that consciousness in some sort of way to make it prone to certain proclivities. And so as time moves forward, those choices will be made and might be not necessarily predicted because that precludes the possibility of free will, but has certain probabilities or possibilities based on the configuration of the universe, the whole universe, actually, in general. So, when you think about it, that's not completely nonsensical, right? So I don't know, what those proclivities are, that becomes maybe non-scientific because it's just based on, I guess, observation, empirical. It's still, I guess, that's kind of scientific. It's empirical observation, but over tens or thousands of years, or hundreds of years of looking at people. And so, who determines that? I don't know how that was initially determined, but still, the idea that you have an initial condition and it affects the possibility of the system moving forward is straight up science, and we do it all the time. So just putting that out there. But so, I sometimes bring this up because when I was first learning this, I mean, one of the things that is, as I told you early on, or maybe that was again mechanics, is you kind of try to find your strengths and weaknesses as a scientist. And my mathematical abilities aren't the best, but I definitely have an intuition that I see patterns. And one of the things, and as we talked about at the first beginning of the course, is that the universe, these patterns are not accidental. These symmetries, as we call them. And I'm not speaking, just geometric type symmetries. I'm talking about the ways in which quantities behave according to certain physical laws. But then in completely different scenarios, you see maybe somehow these similarities or symmetries in the way that physical laws, physical quantities interact based on certain physical scenario. Anyway, that's something that jumped out. So that's what we're doing. We have to apply the boundary conditions and we figure out what this constant specifically is in terms of our initial conditions. And it picks out of all the infinite solutions, which this equation 16 represents, the one solution that applies to our problem, which then dictates how the system will behave as time progresses. So that's the pattern. That's the deal. So applying the initial conditions, what are the initial conditions? Well, it was that at t equals 0, the current was a maximum and the charge was 0, or was a minimum at 0. So yeah. So let's apply the charge first. So because that charge is there's no current term in this. So basically the boundary condition is that, or initial condition, boundary condition meaning bounding the problem or whatever, but it doesn't sometimes make sense with physics. We just say initial conditions, but the initial conditions of the circuit is that at t equals 0, Q of t, charge on the capacitor, equals 0. So we apply that to this problem. At t equals 0, Q of t is equal to 0, and then solve it, and that will give us the value of the constant. Watch. So this term over here is just 0, and that equals log of E of C plus 0 plus chi. So for my problem then, I'm not going to erase this, sorry. For my problem, for this problem for me, chi, my constant chi, is going to be equal to negative log of E times C. So I basically take that and put it back into the equation here. So my specific solution is this minus T over RC is equal to log of EC minus Q over T minus log of EC. I'm going to use that identity. Log A minus log B is log A over B. So we're going to get minus T over RC is equal to log quantity EC minus QT over EC. And now I'm going to take the exponent of both sides of the equation because I want to get rid of that log. If I take the exponent on the right side, then I just have E to the minus T over RC, minus T over RC. And on the left side, it just takes the argument out. I just end up with E C minus Q T over EC. And let me just remind you of those aside. Remember that, so I use 2. This guy from here to here is that log A minus log B is equal to log A over B. And the exponent of the log of A just equals A. So I've applied this guy between 19 and 20, and this guy between 20 and 21. Maybe I should just number those. Make that 22. But I say log of A minus log B equals log of A over B. And exponent of quantity. Exponent of quantity, exponent of quantity what am I doing? Well, yeah, log of quantity A is just equal to A. All right, so I've got this equation here, and I can simplify it now. I can simplify this because I want to solve for Q of T. So I'm first going to multiply. So sorry, I don't know why I started writing this as an E. That's a script E. That's M. E implies electric field. Sorry about that. Okay, so now I'm going to multiply through by EC. So yeah, I'll keep that as an aside. Now we're back to this guy from here. So from 21, 24, we're going to have EC times E to the negative T over, and that's where this, because an exponent has to have a unitless, is a unitless number, and that's where you see that definitely RC have to have units of time, otherwise it doesn't make mathematical sense. And it does. So time, the variable will cancel time, the constant, and you just have E to, so whatever time is transpired, you put it in there and that gives you that quantity. And on the right side, we have equals mth times capacitance time minus Q of T. So again, just keep simplifying. So we're going to have 25. This is going to be E C E to the minus T over RC minus EC equals minus Q of T. Then multiply through by the minus sign. We're almost done. Q of T equals EC minus EC. I just flip around. E to the minus T over RC. Now I can factor out an EC on the right side, and I have Q of T equals EC times quantity 1 minus E to the minus T RC. And finally, the thing that we do is to go ahead and define the time constant now. So I'm going to define tau RC as my time constant for my RC circuit. And that's going to be defined as the capacitance times the resistance. Oh, we had a fluctuation there. The get it back. It's still there. Uh, hmm. Are we still there? That was interesting. So we had a fluctuation in the, I think that happened before earlier in class. That's what happened. Had a fluctuation in the power for some reason, and it knocked out our other two connections, but the phone connection, it didn't. I guess because it's a phone, so it has, you can switch to the phone service opposed to the Wi-Fi. Where my other two computers are connected to the thing. So I guess they'll be back. I guess I can just keep going because this doesn't seem to be interrupted. Maybe those other two will come back momentarily. There you go. All right. So yeah, I can now write my equation 27 in terms of the time constant. So if I do that over here, I actually like this way better. It's longer, but I haven't had this yet. And this is the way they're going to do it in the math class. They won't use the shortcut. So to show you separation of variables again, like this. All right, so I'm going to plug 28 into this guy. So my full differential equation, my solution, is, and I've already erased the differential equation, didn't I? Yeah. But so 29, my differential equation, my solution Q of t is going to be equal to basically the maximum charge on the capacitor, which is the voltage of the battery times the capacitance, making sense. And then the rate at which it's charging kind of falls off exponentially. 1 minus this term e to the minus t over tau RC. Yeah. So that is the solution. And it has certain characteristics that we saw something like that with the drag problem, actually. And the rate at which the acceleration was changing. It also fell off exponentially, just like this, in the same form. If we graph this, the graph looks like this. And so they'll have this in the book for you. So we know that our capacitor is going to reach a maximum charge. But technically speaking, it doesn't do that until you get to infinity because of this exponential. So for example, if the maximum charge on the capacitor is this, well, it's this value, E times C, but if on my graph, that's this, EC. And by the way, this is time. So time is my independent variable in seconds. And this axis is the charge in coulombs. Time. Charge QT. And the units are coulombs. So sure, basically, whenever this term is 0, this whole term becomes 1 because e to the 0 is 1. And, wait a minute, what? Wait, what am I saying? No, e to the yeah, e to the 0 is 1, but e to the infinity, this whole term goes to 0 because this is a negative sign here, right? So you could remember that uh, you could write this term as e to the minus t over tau RC is the same thing as 1 over e to the time divided by tau RC. So as time increases, this thing blows up and the whole number goes to 0. So that doesn't happen though until t goes to infinity. This is not going to be number is not going to be 0 until this number gets to infinity. So technically that means that, and so when that's 0, then that's when this uh, charge reaches its maximum capacity, meets maximum charge. So technically speaking, it's saying that that won't happen for any circuit until you get to infinity, but that's not practical because we do it all the time. So basically, at what point does the charge stop changing? What there's infinitesimal changes to the charge on the capacitor such that it's basically negligible. Well, as it turns out, the time constant gives you an example of that, or gives you some sort of qualitative estimation of that. Because again, here's the maximum charge, and that maximum charge is represented by this line here. And if you were to plug this function into your calculator, you're going to get a curve that's doing the following. Curve is going to be doing this. And it's just going to, again, it won't get the maximum until infinity. But what we find is that let's take a look at what is the value of the charge at one time constant. So, and how long was that? So, well, we won't know unless we have specific numbers, which I didn't give you here. But um, what is, we can do it in terms of relative charge. So what is the charge on the capacitor after one time constant? Tau RC. Well, if I put tau RC into that thing, I have Q of t is equal to EC times 1 minus e to the minus 1, right? Because that's tau RC over tau RC, or minus C over minus tau RC. That becomes Q of t equals EC 1 1 minus e to the minus 1, right? Because the tau RCs will cancel out. That guy goes. And that's something you can calculate. Just put in your calculator. And it's going to give you a fractional percentage of the, growth of the charge on the capacitor. So you find out that yeah, so basically it's EC times 1 minus 1 over E. And Let me just write this out for you. So it's going to be something like Q of T equals EC 1 minus 1 over E. That's 2.7, whatever it is, 2.718. I mean, you just do it, right? And you end up getting 63. So EC times 0.63. In fact, on the right side, let's just say a time constant. So the time is Q of tau RC. So the way that that's interpreted is that after one time constant, the charge has reached 63% of its maximum value, right? Because I should have also defined over here that I didn't, but I forgot to do that. We can also state that that Q, that the maximum charge on the capacitor, Q max, is the, well, I just do it here, just won't confuse you. All right, I can do it here. I can say that EC is defined as the maximum charge on the capacitor, which obviously makes sense if you think about it. So we talked about the other day with when we had first introduced capacitance a couple of weeks ago. And so and so what this is saying then is that, and you can choose the time constant to be very practical because you have control over that. When you build a circuit, you know what capacitors you're going to use, and you know what resistors you're going to use. So if you use like a 1 milliohm resistor, and I don't know, I have to work it out, but I think like, yeah, it turns out to be seconds. So like a 1 milliohm resistor and a wow, a kilofarad, or I guess how would you say it? 1 times 10 to the 3 farad, 10 to the positive 3 farads would be, no, what am I saying? Oh, I'm trying to get something. Capacitances are, to be practical, they have to be pretty, you know what, I can't remember the numbers, but the point is, you choose your capacitances and you can determine the time, right? So like, oh yeah, I guess if I had like 1 farad capacitor and a milli ohm resistor, then my time constant, I think, will be 1 millisecond. So that's kind of a reasonable kind of time that you would get. And I mean, you could time it for whatever. Like a lot of times you could make whatever. You could make it have 3 seconds. You could do whatever because you just pick the value of the, you have a lot variable diversity on the varying types of resistors that you can use. Practical capacitors in the lab, they're only going to be a certain, value that you can kind of get your hands on, but you could design it so that you get circuits where the time constant is 3 seconds, 4 seconds. So for example, the time constant for 3 seconds, after 3 seconds, the charge were 68% of its maximum value, then you might guess after 3 or 4 time constants, 20, in that case, 3 time constants would be 9 seconds, 4, it would be 12. After about 12 seconds, you're going to be over in this regime for the charge. So whatever changes the charge to the capacitor from that point on are going to be somewhat negligible. So you would say that approximately after about 12 seconds, the capacitor is fully charged. So that's how you handle it. The time constant rates when you can approximate the maximum charge on the capacitor, essentially. Yeah. Yeah. So what's done is, here, maybe if that's a whole, then that's a half. So 63% might be somewhere here. So the way and you probably want to see a graph like this in your book, you might say that, well, at this point here, that represents one time constant tau uh, RC. And the value of the capacitance the charge at that point is going to be this, 0.63. 0.63 maximum value, or just EC, is at this point here. Yeah. Yeah. All right. Now, if this were separation of variables for drag, turns out with that, this first integral would give me the velocity. And it actually kind of, I very much, I don't know why I see the symmetry there. Obviously, charge sorry, charge. Oh, wait a minute. It would give you position. Position? Or no, it would give you, so, and the other way would be velocity. Yeah. Sorry, I don't know. That kind of breaks down, but is that true? Or is it? No, actually, it's velocity. Yeah, you get velocity. Sorry, I'm just rambling on. First, and then you have to do it again to get the position. Yeah. Well, in this case, we've got the charge. If we want to get the velocity, then we have to take the derivative. Sorry, if we want to get the current, we have to take the derivative of this equation. So what you see is that the charge, and it does make sense, right? That if the charge increases exponentially, the current should decrease exponentially. And so you can very easily see that by taking the derivative of this equation. So let's do that, and then also let's plot and show that the current starts at a maximum at time t equals 0, and then dies down to 0 exponentially in the same, with, dies down exponentially, full stop. So go ahead, take the derivative of this, and see if you can do that yourself. And you can always just, to prove what I'm saying here, or to demonstrate, to prove for yourselves, you could plug this function into your graphing calculator and go through this process. And you can do things like, you can prove it, right? You can see what is the value of the current after 3 time constants. So you just make this value here tau 3, and up in the equation, it would be, you're going to get e to the minus 3. So this was e to the minus 1. So that would be e to the minus 3, and then see how that changes. In fact, let's do that. Let's put that in and see how that changes this. So I'm going to end up with, 3e, yeah, and then inverse minus 1 plus, yeah, that's like 99, and so you get 99. If so, in just three time constants, this comes to EC times 0.99. And so it goes from 0 to 100, right? So yeah, it's in fact it's 0.999. So after three time constants, like I said, you practically have a full charge on the capacitor. So that would, and I didn't give numbers here, but like if I designed the, you know, the capacitor to be time constant to be a millisecond, that means in, basically a tenth of a second, you're gonna have, sorry, tenth of a second, no, 9/10 of a second, so 3 times 0.3. A millisecond is, wait, what? Yeah, if it made it 3/10 of a second, so I said 3 milli. So that's really small. I should have said 3/10 of a second. That's what I was thinking in my head, not milliseconds, but whatever. Yeah, if it's 3/10 of a second, then after about a second to be fully charged. If it's 3 milliseconds, then after point zero approximately 1 seconds, which is still pretty fast. Whatever, I think you get the point. Let's go ahead and finish this up so we can go ahead and I guess it's almost time for break. Wait, what? Oh, because I didn't start because this is only like an hour and a half lecture. I didn't start lecturing to 30 minutes in, so that's why we're at 10 o'clock and not 9:30. My bad. I was trying to get that camera straight. I think I started. Yeah, whatever. So, yeah, I have this lecture designed to be about 30 minutes, an hour and 30 minutes. So that's about right. But let's just finish this out, and so we'd be done with it, and then we'll move on to magnetism after the break. So yeah, how do you take the derivative of that? Should be pretty straightforward. So taking the derivative of equation 29, we're going to get that. So it's the d dt of q of t. So it's the chain rule, right? You have, I'm going to multiply this out a little bit. So it's going to be the derivative of a constant times ec to e to the minus t over tau rc. So the derivative of a constant is 0, first term. I'm going to go ahead and convert this to dot notation. So q dot is, prime notation is when you take derivative with respect to coordinates like dx or dy. Dot notation is when you take the derivative of a function with respect to time. So this becomes, first term is 0 and then minus, so that's a constant there. So the derivative of the, what's the derivative of a exponent? Of a thing? It's 1 over tau times, it's the constant times the exponent again, right? We're doing that right. I should just, what I mean, yeah. I guess I've been I say I review all the math, so I should write this up. I don't have it in my notes, but I should put it there so I have it. Let's get rid of all of this. I just feel like I should put it, so it's there. So yeah. So recall the derivative d dx of e to the x is equal to e to the x. I'm trying to write it like you see the math, right? E to the minus x is equal to basically -1 times e to the minus. Actually, let's do it like this: a minus ax. because it's actually 1 over the constant. So that would be minus 1 over a e to the minus ax. Okay. So applying that to this problem, let me put that in my notes because I always kind of forget. Mhm. All right, so I'm going to apply that here in this term. So what that's going to be is I have a minus sign out there already. That's this guy. But then that's going to be times minus 1 over tau RC times e to the minus t over tau RC. So the minus and the minus cancels. So this is going to be from 31. Break there. So this will be 32. No, 34. So QT, the derivative of which is basically just current, right? That's the other thing. The derivative with respect to time of charge is current. So that's just going to be I of t. Right? That's the definition of literally the definition of current. Those two dots might be confusing. Let me just go back to the Leibniz notation or whatever, whoever notation that is. So d dt, yeah, of q of t is defined as I of t. And minus and minus is plus EC over tau RC. So that equals EC over tau RC e to the minus t RC, over tau RC. Not quite done, but remember that tau RC, we define that as just R times C. So I can stick that back in now, and what I get is the current is going to be equal to right, so you can see that EC over RC times E to the minus tau, basically T over tau RC. The capacitances will cancel, and that's going to give me something that has units of current, right? Ohm's law. Current times resistance equals M, or M over resistance equals current. So this really, you can define this as the maximum current in the circuit. So E over R is equal to a constant, which is I max. Some people will write it as that. And same thing with the charge. I could have written that as Q max, right? This could be written as Q of T equals Q max times this stuff, 1 minus e to the minus tau T over tau RC. Yeah, it's the same thing. And then I could write that equation, I max times E. This could be written as I max times E to the minus T over tau RC. But either way, let me just box in these solutions. I'll do it, I can do it here. Yeah, so that the final thing we'll say is that the charge on the capacitor is abides by, this equation. These is the same equation, but then the current the current 38 I of t is equal to I just like I like to write it like that. I don't usually write that I max times e to the minus t over tau RC. Right. And so at t equals 0, you can see that the maximum current is just E over R. And so at which is like I tell you, when you close the switch, the current is the maximum, the charge is 0. You can see it here again. At t equals 0, then that's just 1, right? E to the 0 is 1. And so 1 minus 1 is 0. So at t equals 0, Q naught is 0. At t equals 0, I naught is E over R, which is as it should be. So it's satisfying the boundary conditions. And it's really interesting. It's all set up that way because of way back when we saw that time constant equals ln over E over R, E over C. That's what determined. So that made it so. And it just works out that way with these differential equations. When you do that and you get the final solutions for your equations that define the phenomena, if you've solved correctly for the correct constant of integration, then physically it will match the constants associated with your physical phenomena, in this case, a RC circuit, are the constants that they should be. Namely the maximum current and the maximum charge. Yeah. So if you graph it, then if you put this into your graphing calculator, you will get what you expect. You'll get that it's going to look something like this. I told you. So this is time and this is current, right? So the maximum current is here. That's going to be E over R, right? I max. And, I guess you could put that out there, but basically it's going to die down to 0. So what you see is that this function, when you graph it, it looks like this. And it's going to be 0 at infinity. Now, we still have the time constant. So what does that mean for this circuit? Well, put it in and see. What is the value of the current after one time constant? So you can say that I of t equals tau RC. Well, if I just put in tau RC, I have E over R, right? E to the minus 1 is what that comes out to be, right? Minus basically tau RC over tau RC. So that's going to be E over R, E to the minus 1. And our current then 31, 33, 39, 40, 41. Um, what am I saying? Yeah, what is that? Just put it in and see. Sorry, I'm a little bit mentally distracted today for some reason. Yeah, yeah. So you end up getting approximately 0.37. So you can I of t is equal to uh, approximately 0.37 of the maximum current. So again, half, it's 0.37 of max. So it's down here. Yeah. So yeah, so you get for this, it's after one time constant, the current has died down to only approximately 37% of the maximum. That might be someplace like this, so tau RC, and over here, I've got 0.37 of the maximum current EOR. And you should see those graphs in your book as well. So again, after, if you put in, 3 time constants, this is probably going to be down to, basically zero, because it works. And it works. It's not an accident that on this guy you've got, well, I guess I've erased it already. I was 0.67, 0.63, and this is 0.37. So mathematically, you get that kind of symmetry between the solution and the derivative of the solution. All right. I'm interested to see where they have this in your book. I'm pretty sure that all books cover this in the chapter some way, but some books do it more explicitly, more. But I've given everything, so I've shown all the steps in probably more detail than what they normally would do. So yes, this is your chapter. Your book. In the book. This would be the field, capacitance, resistance. Going to be in this circuit somewhere. Circuits, ammeter circuit, loops, RC circuits. Here we go. It's the last thing in the chapter. So, and there you go. Those are the solutions. So that's how they got them. I'll show you. So that's charge, and this is the current. And this is at Q naught, QZ. Well, yeah, that's just the Q naught is just Q max. So oh, we have to do a discharging capacitor too. So yeah, this is charging, and these two are charging, and these two are discharging. I forgot about that. Yeah, I forgot about that. Okay. Well, I can let you do that actually. I guess that's what I normally do. That's what I don't have in the notes because discharging capacitor. Maybe I could do that as an aside or something. It's it follows the same basic pattern as what we just did here. I just set that up for you. So it's kind of like going back to that circuit then, at some point it may take longer, but the capacitor will be charged, right? At some point. And so let's come back over here. So you have a full charge on the capacitor and the current stops because for the same reason it did before when we talked about the charging capacitor. So this was the circuit that I had. So I have a switch, I have a battery, I have a resistor, and I have a fully charged capacitor, right? So I open the circuit, I take the battery out, and then I close the circuit back up again with just the fully charged capacitor in it and the resistor. Well, what happens? What happens? What happens is that the capacitor acts like a battery. It discharges and the current goes around in the opposite direction. But it dies, it doesn't, yeah, it basically all the energy then dissipates because there's no battery in the circuit to replenish the energy, the current just dies down exponentially and goes out to zero. So how would you solve for that? The solution in that problem? Same thing. You do the same thing we just started. You start off with the voltage rule. So you can go around. I'll go around in the direction of current. So I'll have by going through. Remember, this would have been the orientation of the current is established by the initial condition. So before I took the battery out, so the positive direction of current was around this way, was counterclockwise. So now the current is going clockwise. So that's kind of a negative current based on the original situation. We'll get to that in a minute, later at the end. And that's where that negative sign comes out because you're going to get the same current. The functional form of the current is going to be the same, but they just have a negative sign there. And that's why, because it's going around in a different orientation than initially. So that's what the negative sign means there. Here we just do a voltage analysis to start the problem, just like we always did. You can start anywhere. I start here. And if I go around clockwise, then when I go from here to here, again, that's a voltage gain. So I'm going to have that the voltage is equal to the capacitance divided by the charge. And then I go through the resistor in the direction of current. And I have the battery in the opposite direction before I take it. Can't remember. Because I got to get the same signs here. So I'm trying to think. I times R. Sign convention. By placing the battery in the orientation that we previously chose, we established the positive direction of current to be clockwise. I of t. Since the capacitor drives current in the opposite polarity, we say current is negative from the discharging capacitor as compared to the charging capacitor. Oh, right. Okay. Yeah, there's two negative signs. That's tricky. Because here there's a plus. Because if I traverse in the clockwise direction, start at this point and traverse around, I go from minus to positive, so I'm going up the potential, so that's got to be plus right there. But then technically what we say is we go through the battery. If we traverse the battery in the direction of current, we have a voltage drop. So minus basically I times R. But the current is minus relative to the original, that orientation. So there's another minus sign. I don't know how to write that, but I'll just say it. And so you get a minus and a minus, and it should be plus, which it is. So maybe I do it like this. So minus, but then minus I of t, yeah, times R, and then go all the way back around and then back to zero. So ultimately, then I just have, I should remember this, so this would be 39, and 40. So ultimately, this is the differential equation I'm solving. Q over C, then plus I times R equals 0. Remember, these are time dependent, and this can be defined in terms of charge. So what this really is 1 over C Q of t plus d dt Q of t times R equals 0. And then you're back to doing separation of variables again. So then 42, you divide through by RC, and you got 1 over RC Q of t times plus d Q dt equals 0. And then you can go through and separate variables again. Yeah. So you're going to have, what I'll go ahead and finish. So 1 over RC Q of t equals minus dq over dt. And so I just cross multiply and take the minus over, and I'm back to 44. I have a minus dt over RC equals plus dq over of t over q of t. I'll go ahead and finish this out because it's just simple. So, and that we're done, right? Because now we're back to that same, it's separated, but here I don't have a complex type of function. So it's just going to be straight log. So for the discharging capacitor, I'm going to get minus 1 over RC times T, plus a constant. And over here, I'm just going to get log of Q of T plus a constant. Constant 1, constant 2. So we can go through and do that manipulation stuff again, but in the end, you get this solution that Q of T is equal to basically EC over E to the minus tau RC. So for the discharging capacitor, that's the solution now as opposed to this. And the current is going to be the same. We just take the derivative of that, and you get the same solution, but just the minus sign is there. Which indicates that the current is just so, yeah, if I take the derivative of that, then I'm just, that minus sign is going to pop out. And so I'm just going to have I of t is equal to minus E over R, E to the minus tau RC. So, yeah. So these two solutions are for a discharging capacitor, what it's called, discharging capacitor. And these two solutions are when the capacitor is charging up. Okay, so 29 and 38 are for a charging capacitor. And I didn't number these, but I guess 45, 46, and 47. So 46 and 47 are for the discharging capacitor. And the negative sign here just means that the current is going in the opposite orientation when the capacitor is discharging, as opposed to the circuit when it's charging. And if I, graph that, it's going to look the same as the other one. Just, it's just current doesn't have a direction, right? So it's a scalar quantity, so the magnitude will be the same. So when you graph the function, the function of the graph will be the same. But this graph is a little different. This graph now looks kind of like, it looks kind of like it's charged, but it looks kind of like this. It discharges, goes to 0. And you can show that. So they have that in the output they're showing here. Oh, really? Oh, I didn't change the book back. So hopefully you can see me from the other camera. I don't know if that's the case. Is that the case? Um, yeah, I think those other cameras were still in place. That one. But sorry about that. But yeah. Circuit. So yeah, these are all the solutions, and they just go through and they don't really derive them for you. They just kind of explain and give you the solutions. But I've derived them. Well, they do. They give the that's the discharging, the voltage rule. Looks a little different. And the charging one was here. And that's what they solved. And they gave you the solutions there. So there you go. Checkpoint. Oh yeah. So here's that stuff that they're doing when they solve it. Yeah. So they're doing the CADE particular solution for the difference. So all that stuff is what I explained earlier. And they're picking out the family of curves, blah, 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 blah. Yeah. Okay. What is this? Oh, potential energy? Hmm. That's an application. Are you looking at how the energy changes? Yeah, I think so. Yeah. That's the energy function. Okay. I'll go ahead and read through that. That's probably worth doing. Yeah. And there you go. You're at the end of the chapter. So I would do that last example problem. I would read through that. If you have any questions or something about that, you could talk. But once you have the charge, like because we had the three different functions, it's just a matter of plug and chug because we defined the energy in a capacitor in three different equations, and a couple of those equations have the charge in them. And so uh, because we've defined the charge here, then the potential energy is it's a time varying charge now. You just stick that into potential energy equations that we had where there's charge, and that's how you're going to derive the equation that they have there. So it tells you that the energy is changing exponentially as well in the function. So, sorry, get back to this. Yeah, it's telling you that the energy is changing in the function exponential. So everything changes exponentially, the charge, the current, and of course, now the energy, because charge is dependent upon energy in some way, based on those equations that we derived last week or whenever it was. All right. So I love these problems. These are boundary value problems, and you can apply them to all kinds of things, like how they do population growth, um, drag, drag problem in physics. Yeah. Or we'll have something similar when we get to inductors, RL circuits and RLC circuits. They all involve this kind of, applying voltage rule, getting a differential equation, and then solving that differential equation with some method, the simplest method being separation of variables. All right, break time.